Today, we're going to talk about precision and accuracy. What's the difference? Those two words are commonly used interchangeably, but in science, we have very specific definitions for those two words. Accuracy is how correct or true a measurement is. If I take this meter stick and measure the width of the board and tell you that it's 81 centimeters, that's an accurate or true measurement. Precision is how detailed, how exact a measurement is. If I was more careful with the meter stick, I could tell you more precisely the width is 80.7 centimeters. So accuracy is how true or correct, and precision is how exact a measurement is. The instrument you use to make the measurement limits the precision of the measurement. It wouldn't make any sense for me to tell you that the width of this board was 80.715892 centimeters, because this instrument doesn't have that kind of precision. It can't tell you that many digits. A meter stick, for example, cannot make a more precise measurement than a fraction of its smallest division, so which for the meter stick is 1 millimeter. These tiny black marks are 1 millimeter each. As a general rule, an instrument's precision is limited to 1/10 of the smallest division on that instrument. So for example, if you had, well, that was loud. If you had a triple beam balance as I have here, the smallest division on that is 1/10 of a gram. And so the precision of that instrument is limited to 1/10 of a gram, which is 100th of a gram. For the meter stick, you might only be able to tell to the nearest half millimeter or so, not quite down to 1/10, but on that same order. Everyone's favorite subject, significant figures. We use rules for significant figures to write down a measurement so that anyone looking at that measurement will know the precision or the limit of the instrument we used. Every measurement has the same amount of error. Every measurement has some amount of error. And the rules for significant figures help us and others know the limits of our measurements. Remember the 4 rules for significant figures on the next board. Rule 1. Any non-zero digit is significant. 22 grams, they're both non-zeros, both 2s. Those are both significant. That number, that measurement, has 2 significant digits. Any zero between 2 significant figures is also significant. So if I have a measurement of 101 meters, that 0 is in between 2 significant digits, 2 non-zeros, and so it's also significant. Number 3, ending or trailing zeros are significant if they're also after the decimal point. So this measurement here, 44.10 seconds, because that 0 is at the end, it trails at the end, and it's after the decimal point, it's also significant. So this measurement actually has 4 significant figures. And the last rule, ending or trailing zeros are not significant if they appear before the decimal point. So for example, in this measurement, which is close to the speed of light, at 300,000 kilometers per second, that last 0 is before the decimal point and it's not significant, and therefore the other zeros aren't significant either. So this one just has 1 significant figure out of all of those. Here are some examples. How many significant figures are in the measurement 88 days? Well, we have 2 non-zero digits, and so according to rule 1, if it's a non-zero digit, it's significant. So this one has 2 significant figures. How about this measurement, 525,600 minutes? It has a 0 at the end. It has 4 non-zero digits. Those are definitely significant. But what about the 0 at the end? Because that 0 is before the decimal point, it doesn't count as a significant digit. So this only has 4 significant digits. The 5, 2, 5, and the 6 are significant. 365.250 days. All the non-zero numbers are significant. There's 5 of them. And we have a 0 and it's at the end. And because it's at the end and after the decimal point, it's also significant. So this one actually has 6 significant figures. 6 significant figures. How about this one? 15,000.0 grams. 15,000.0 grams. That 0 is at the end. It's a trailing 0 and it's after the decimal point, so it's significant. Additionally, because that 0 is significant and the 5 is significant, all the zeros in between are significant too. So this one has 4, 5, 6 sig figs also. Sometimes I just say sig figs instead of significant figures. For most of our work in physics, you will only need to use the rules for multiplication. I'm sure that you remember these from chemistry, but the ones for multiplication, that's when we're going to use the most, and so that's the one I'm concerned about. And that rule is simple. When multiplying or dividing, your answer should have the same number of significant figures as the least precise value used. And we'll be working on that in the classroom together. Good. I just knocked the board off. What if you measured something to the nearest centimeter and the length was 20 centimeters? To indicate that that last zero in the 20 is significant, because right now it's not. Remember, it's an ending zero and it's before the decimal point. So if I write 20, that only indicates one significant figure. But to indicate that that last zero is significant, you would convert to scientific notation. It's pretty simple. So 20 centimeters is the same thing as 2.0 times 10 to the first, and everything that you write in scientific notation is significant. So if you write 2.0, that's 1 and 2 significant digits, and so you've got that. 120 minutes, if you wanted that to have 3 sig figs, you would write that as 1.20 times 10 to the second. 10 to the second is 100. So this is 120 also, but I've written 3 digits in scientific notation, and because it's in scientific notation, they're all significant.